Hi, my name is Marcin, and today I will present our paper called MisConv, Convolutional Neural Networks for Missing Data. Convolutional neural networks are the go-to models for image processing tasks. However, in practice, it often happens that parts of images are occluded and therefore missing. It is not yet clear how to adapt CNNs to process such images. The most common approach is to impute the missing fragments and then process the image as if it were complete. However, this presents a problem. The uncertainty of imputation is lost on the model performing the downstream task, which may worsen its performance. In this work, we present MisConv, a generalization of CNNs to the case of incomplete images. We will show that MisConv takes the uncertainty contained in missing pixels into account and allows for training well-performing models on incomplete data. Given a neural network which processes images, MisConv modifies only the initial convolutional layer of that network. From a high-level perspective, an incomplete image is processed in the following steps. First, we model the distribution of missing pixels with a mixture of factor analyzers model. Then, we calculate analytically the expected value of the convolutional operator applied to both known and unknown regions of the image. Thanks to this step, the distribution parameters are transformed into a numerical vector, which can then be processed by the further layers of the neural network, regardless of the task they perform. We represent the missing parts of an image with a probability distribution. Such representation takes into account the uncertainty of missing data estimation and should be more reliable than a single imputation. As a probabilistic model, we use a Gaussian density represented in the form of the mixture of factor analyzers, which is well suited for modeling high-dimensional distributions. Given a random vector z and a linear convolutional operator m, we first calculate the MFA density of m applied to z. Then, we calculate the expected value of ReLU activation applied to mz, obtaining a numerical vector, which can then be processed by the next layers. We tested the MisConv in the task of training various computer vision models on images with previously randomly removed missing fragments. We trained models for classification, reconstruction, and generation. In practice, for modeling the MFA distribution of the missing pixels, we used a deep MFA neural network, which was a prior work of ours. MisConv was compared with other methods of dealing with missing parts of images, such as zero imputation, KNN imputation, imputation with an arbitrary conditional flow, as well as processing the incomplete image through partial convolutions. As a first experiment, we trained classifiers on incomplete MNIST, SVHN, and CIFAR10 datasets. When tested on incomplete images, MisConv performed better than classifiers trained with other imputation techniques. We also checked the performance of classifiers on complete data and found that apart from MNIST, classifier trained with MisConv does the best job in adapting to complete images. In the next experiment, we trained Wasserstein autoencoders on incomplete MNIST, SVHN, and Celebay datasets. We benchmarked their ability to generate images as well as reconstruct them. In most of the cases, model trained with MisConv emerged as the best one. One could ask a question: isn't it enough to use the mean of the MFA distribution as a single imputation? Turns out, it is not. We can see that MisConv models which take both mean and the variance into account do better than the models which used only the mean of the MFA distribution. The convolution filters learned by those models are able to distinguish between the known regions of the image and the fragments for which the distribution had been used. Our hypothesis is that this allows models trained with MisConv to treat those fragments with higher uncertainty and rely more heavily on their originally known image parts. In conclusion, we introduced MisConv, a general mechanism for adapting CNNs to missing data, and presented a theoretical background for this probabilistic approach. We verified this approach experimentally, achieving results better or comparable to other previously known missing image processing methods. Thank you for your attention. Feel free to check out our paper or reach out to us with any questions. Happy conference!